Hi, this is Robin, and in this video we'll be going over the pre-check questions for discussion 7, single cycle data path. Combining everything that we've learned up to this point, we can start looking at how our CPU works. So we can think of our CPU as containing two parts, the data path, which is this top part, and our control logic, which is this bottom part. The data path contains the hardware necessary to perform our operations, whereas the control tells the data path which operations to do. Also, our data path controls enough hardware such that it is able to execute all RISC-V instructions, and it takes one cycle to perform each instruction. So the single cycle data path must have hardware to do our immediate generator, our branches, and our memory, and so on and so forth. As you can see here, we can split up the data path into 5 main stages. We will go over these stages more in depth in the next part of the discussion worksheet, but as a brief overview, the instruction fetch gets the next instruction that we want. Instruction decode identifies the instruction and whatever registers, immediates we need, as well as determining whether we need to branch, read or write to memory, and so on and so forth. The execute phase is where we have the ALU, or the arithmetic logic unit, and then our mem access is mostly used for loads and stores where we read or write to memory, and finally the last stage being write back, where we write back our desired results to our register. Okay, now the first question states that the single cycle data path makes use of all hardware units for each instruction. So remember that because this is a universal data path, it includes everything that any instruction needs. So including memory, branching, immediate generation, and so on. However, as we know, not every instruction needs these parts. So our answer is false. All units are active in each cycle, but their output may be ignored by control signals. What does this mean? This means that at any point of our data path, there's always going to be data sent along these wires. However, thanks to our control unit, we know which outputs to ignore and which outputs to use. So let's take a look at add as an example. So, as you know, add takes in the values of two registers and then adds them together and writes it back into our RD. And we do not need to access memory at any point of our add instruction. However, this memory portion of our data path is still technically active, so it will actually still output some data into this mux. Thanks to our control logic, our mux will select the output of our ALU to write back into our register. So we effectively ignore the result of reading from memory since we don't need this. Remember, the control logic is the brains of the operation. So once we decode our instructions, we know which instruction it is and which registers to use, how to interpret any immediates, and what the ALU should do. The second question states that it is possible to execute the stages of the single cycle data path in parallel to speed up the execution of a single instruction. So what it means by executing the stages in parallel is that we can run these 5 stages at once to save some time in executing our instructions. However, we cannot run the stages in parallel because each stage depends on the value produced by the stage before it. So, for example, we first need to fetch the instruction before we can decode the instruction. And only after we decode the instruction do we know what values go into the ALU and what the ALU should do with these values. And in the case of memory access, such as loads and stores, we only know what the address that we want to access is after the ALU has performed its actions. Finally, we can only write back to the register once the memory access has gone through due to the possibility of a load word. Therefore, these sections cannot be run in parallel for a single instruction. And then the last pre-check question states that combinational logic is only used in the instruction decode stage. So combinational logic includes ands and ors. So it's false because a lot of our muxes use combinational logic to determine which of these inputs it should output. So all of these muxes use combinational logic, and we also use combinational logic in the ALU to determine whether we should have read or write enable and whether we should branch. So combinational logic is really prevalent throughout our data path and is necessary for our entire data path to work. And that concludes the pre-check questions of this discussion.